He's joining us from Wisconsin, and he will talk about Hamilton's Ricci flow.
Okay, thank you for the introduction. And my talk today is, topic is Hamilton's Ricci flow. So I'll give a brief introduction of the Ricci flow and some progress and the recent progress of that. So one of the important questions in geometry is to find the classical metric. And one of the especially interesting kind is the Einstein metric. So we consider a Riemannian manifold if it satisfies the elliptic equation such that the Ricci curvature is equal to some constant lambda times g, which lambda is a constant, then we can see that this is an Einstein manifold. And one of the important questions is what kind of manifold can we find such an Einstein manifold? This is an extremely difficult problem. So in order to solve this problem, in early 18th, Hamilton introduced a Ricci flow method. So instead of considering this elliptic equation, so I say that elliptic because if I write everything in terms of the harmonic coordinates, then this is basically an elliptic equation on the metric G. So instead of considering the elliptic equation, we consider the parabolic equation. That is the definition for the Ricci flow. So we consider the metric evolved by the -2 Ricci and with the initial condition of any given metric. So we consider this parabolic equation on any Riemannian manifold. So we want to know its behavior when we evolve this under this parabolic equation.
Really on n times r, right? So g depends on an extra variable t.
Yeah, right. This g depends on t. And so is this Ricci curvature. So let me first of all give you some examples. The easiest example is the flat space, that is the standard Euclidean space with the standard metric. So since it's the Ricci flat and it's always steady and stationary under this parabolic equation, so it's a stationary point. Now sometimes we will normalize the Ricci flow a little bit by renormalizing the time parameter. And by doing so, we can consider the normalized Ricci flow, where we have an actual constant, -2 Ricci minus lambda g, and with the same initial condition. So actually, those two definitions are equivalent as long as we do the renormalization of time parameter. And in particular, that means the Einstein manifold, Einstein metric is a stationary point for the Ricci flow. Okay, now another example is the standard sphere with standard sphere Sn with the standard metric. Then under the Ricci flow, since it always has the positive Ricci curvature, then the sphere will shrink to a point. So the graph looks like this. So I have a sphere, then under the Ricci flow it will shrink until it becomes 1 point. So basically under the Ricci flow, if the initial condition is the standard sphere, then the Ricci flow only exists for a short time. So at finite time, the flow will become singular. That means at some point, the Riemannian curvature becomes infinity. So there's only 1 point in this case. Now, another example is the cylinder. So with the product metric. So that means we have one flat direction. So, and this direction won't change under the Ricci flow, but for the first component, that is S2, and it will shrink like the second case. So for an entire cylinder, it will shrink to a line. So we have a cylinder in the first place, then under the Ricci flow it becomes thinner and thinner until it reaches to one line. So it becomes completely singular. Okay. So one class of interesting question is what can we get when we evolve the Ricci flow on any Riemannian manifold? But such problem cannot be answered completely unless we add some initial condition. So since the Ricci flow is a kind of parabolic equation, it actually preserves some nice geometric quantities like the scalar curvature. And if originally I have the positive curvature, then under the Ricci flow, this condition will be preserved. And so it was originally proved by Hamilton in 1982. And he proves that for three-dimensional closed manifold, if originally the Ricci curvature is positive, then under the Ricci flow, it will converge at the first singular time to a standard space form. So that means for three-dimensional closed manifold, if originally the Ricci curvature is positive, then under the Ricci flow, it will converge to a standard space form. Now here, the convergence is true after we perform some normalization. So I simply write it like this. So that means if the time t is sufficiently near the singular time, then the curvature will become more and more homogeneous until at the singular time it will converge to exactly the space form. That is the constant sectional curvature space. So not only we can show that the Ricci curvature, that is the positivity of the Ricci curvature is preserved, but also we can show that originally this manifold M3 is diffeomorphic to a space form. So if we assume that it's simply connected, so it's exactly the S3. So this is one of the topological consequences for this theorem. Now later, similar theorems are proved by Bohm and Wilking in 2006. So they generalize this result to n-dimensional space, so n-dimensional closed manifold, but with a stronger curvature assumption. That is, if we assume that the Riemannian curvature is positive, then the Ricci flow becomes singular at a finite time, and the flow will converge to a space form in n dimension. So in particular, if it's simply connected, then we can say M.
So you have to make clear what you mean by Riemannian positive. You're talking about the curvature, positive curvature operator, and not positive sectional curvature.
We regard this Riemannian acts on the two form, and it's positive on the two form, right?
Yes, that's usually called positive curvature operator.
Yeah, positive curvature, not just the positive sectional curvature, but the operator is positive. So this is indeed stronger condition.
So for 3 dimensions, is there any relation?
Yes.
Yeah.
Yes. So in fact, it's the same.
Yeah.
Intermission 3.
So based on this result, the Brandel and Sean proved in 2006 that the 1/4 pinch differential theorem, differential sphere theorem is true. all those results are true if we assume that some positivity of the curvature. The ideas are similar, so we think. So the statement. Since I only have 20 minutes, I'll quickly. Right.
Don't write it. Just say it.
Oh, the one-fourth pinch means at any point the sectional curvature is greater than, for example, after some rescaling is greater than 1/4 and less than or equal to 1. So at any point, so then it's diffeomorphic to a sphere. Yeah. Okay. Now, like I said, we can prove all those results by using the maximal principle, but they have different level of difficulty. For example, for the Bowman-Wilkins result, we should carefully check the algebraic structure of the Riemannian curvature. Okay, so this is one aspect of the Ricci flow if we assume some positivity of the curvature. Another aspect is the breakthrough of Perelman's work. Now, for the Ricci flow, the Perelman introduced a useful functional that is called the mu functional. Now, I'm not going to write down the definition for the mu functional, but the good news is Perelman proved that the Ricci flow, under the Ricci flow, the mu functional is increasing. So mu is increasing under Ricci flow. In other words, the Ricci flow can be regarded as a gradient flow for this functional. And the critical point for the mu functional is called the Ricci shrinking soliton. Now, by definition, the Ricci...
You have negative Einstein, that would still be.
Actually, the Ricci shrinking soliton is a generalization for the positive Einstein. So let me write down the definition first. So this is the Ricci plus the Hessian of a potential function f minus g over 2 is equal to 0.
What I meant is that initially one doesn't show that it's Ricci solitons are the critical points, and then you show that they're actually trivial except in the shrinking case. That's a sort of two-step statement.
Yeah, right. Now, the Ricci shrinking soliton is very important when we do some analysis for the singularity of the Ricci flow. So if the flow becomes singular, so we can use the point picking method to analyze some high curvature region such that it can be approximated by a given Ricci shrinking soliton. So the classification of the Ricci shrinking solitons is very important. Now, like I said, the key point in the Ricci flow is to analyze the behavior for the singularity. And this can be done by do the classification for the Ricci shrinking soliton. It can also be done by other methods. Now, this question is well understood if the dimension is equal to 3. So for the singularity, I mean the high curvature point along the Ricci flow, especially when it becomes singular. So with three-dimensional, so when the dimension n is equal to 3, the high curvature region is well understood. It's either a cylinder or a cap of the cylinder. Maybe I should add a compact component, which has the space form topology. So this is the breakthrough made by Perelman. He had done the completely classification for the high curvature region. So based on this result, as long as the high curvature region is well understood, we can actually perform the surgery to continue the Ricci flow. That means I can cut off all the high curvature part, then to add some standard top, then I can continue the Ricci flow. Well, but the open question is, what about the higher dimension? Now, I'll talk about some open questions and some progress about the Ricci flow, especially in dimension greater than 3. So the first question is, we know that if the Ricci flow becomes singular at some finite time, then the Riemannian curvature will become infinity, at least at one point. The question is, can we weaken this condition? That is, can we use some weaker curvature condition to replace the Riemannian curvature? So this is a conjecture made by Professor Chen, and he says that if the Ricci flow has a singular time t, then the scalar curvature will blow up. So RT will blow up. So in other words, that means if originally we assume that the scalar curvature is bounded, then we can continue this Ricci flow through this time t. So that means we can do the extension. Now this conjecture, I should write down this as a conjecture. Now this conjecture actually is very difficult. Now the partial progress was proved by Chen, Wang, and Baumler. They have proved that if the scalar curvature is bounded, then at the first singular time, then the Ricci flow solution will converge to a singular space with codimension 4. So if R is bounded, then this will converge to a singular space. No, we don't need to rescale. We don't need to rescale. Yeah. So it should be a length space. And this can be regarded as a parabolic version of the classic Chigger-Coding neighbor theorem. So they prove that if the Ricci curvature is bounded, we have a singular space with codimension 4. But the important thing here is we only need to assume that scalar curvature is bounded, that there's no assumption on the Ricci curvature. But still, I can prove that as long as this is the Ricci flow solution, we can converge to a singular space with the similar properties. Now, in particular, so personally, I think this conjecture is true, is false when n is greater than 4, but it's true when n is equal to 4. So in particular, that means when n is equal to 4, their results shows that if we assume that scalar curvature is bounded, then it will converge to an orbifold. So with some extra work, it's actually an orbifold. So the question is, can we improve these results by removing all the isolated singularities? Whether or not n is equal to 4 is true. So I think I'm going to stop here.
Questions or comments?
Can you summarize the progress in dimension 4?
Now the recent progress is it will converge to an orbifold. So in particular, that means
Boundedness assumption?
yeah, under the scalar curvature bounded, and the energy is bounded. And the energy is bounded. That means the Riemannia squared, the integral of the Riemannia squared is bounded along the Ricci flow. Then we can use the classical way to prove it converges to an orbifold.
The limit orbifold means that it's a smooth orbifold matrix?
Yes, smooth.
Why do you think it's false in higher dimensions?
I do not have the exact reasons. Maybe the similar result is forced in mean curvature flow. Like in mean curvature flow, if the mean curvature is bounded, then we can do the extension. This is another conjecture, but it's false. So we assume that the Ricci flow would be false either.
So in real dimension 4, if you just look at the Kähler case, at least in the negative case, I think you can actually come up with examples where there actually is such a limit, right? If you just follow Kähler-Ricci flow
if it is for the Kähler-Ricci flow, then if scalar curvature is bounded, then we can do the extension. I mean, this conjecture is true for the Kähler-Ricci flow.
In all dimensions.
Yeah, in all dimensions.
Capital T is finite, not infinite.
Yeah, the capital T is finite.
Oh, I see.
It's a very nice problem.
Okay.